We've got a great big radioactivity question next, which pulls in a few bits from elsewhere as well. So have a go at this one. Okay, so the number of neutrons in the isotope. So we've got plutonium decaying into uranium and an alpha particle. So that means we've got 92 down there and 234 up there. But it does say it wants the number of neutrons, not the number of nucleons. So the number of nucleons, protons and neutrons, minus the number of protons is 142 neutrons. Okay, now we want the kinetic energy of the alpha particle. Now we're told that, we're just told it in MeV, so we've got to convert 5.6 MeV into joules. Now remember, 1 electron volt is 1.6 times 10 to the minus 19 joules. So this is going to give us 8.96 times 10 to the minus 13, but we should only have 2 sig fig, so I'm going to round that to 9.0 times 10 to the minus 13 joules. We're using the kinetic energy formula next, and so we get this. We've used our unrounded value there, remember, but rounding to 2 sig fig again at the end. Okay, and now things get a little bit more interesting. So we're told that the power is 62 watts. Now remember, that means 62 joules per second is being released. And so we know that this much energy is being taken away by each alpha particle. So if we know how many alpha particles per second are coming off, we can multiply it by this, and we need to get 62. Right, but the number of alpha particles coming off every second is the activity. So what we're saying is that the power is equal to the energy from one decay times the number of decays per second. And leaving you to rearrange, that gives an activity of this. Remember that you write your I've rounded to 2 sig fig again, but I leave it like that because it's a show that question. Okay, we've got a long way to go yet with this question. Now we're after the decay constant, and it's important to remember this formula for the decay constant. People often forget that one. That's the one we want here because we are told the half-life, it's 88 years. So converting the time to seconds first of all, and then putting it in the formula, and rounding to 2 sig fig to agree with the time at the end there again. Now we are continuing with the decay, and again I think this little formula is one that gets forgotten a lot as well. Remember, we have worked out the initial activity of our sample, and we've got the decay constant now, so that means we can work out the initial number of nuclei in our sample as well. And leaving you to do the rearranging there, 2.8 times 10 to the 23 nuclei, and then we want the mass. So I have taken my own advice, and when I got into the exam I have written down this formula that you'll remember from earlier in the videos, and also that one. So using 1 we get the number of moles, and using the molar mass up there, which is given in kilograms because physicists are civilised, we get an answer there of 0.11 kilograms, 2 sig fig at the end. And that is that question finished.